Assalamualaikum and welcome to the video. I am Muhammad Hafizul Hafiz bin Hussein from Physics Unit KMPK. Welcome to the second video of the series. I hope you are having a great time at the college. In the previous video, we have looked at how to determine the uncertainty of measurement and how to calculate the uncertainty for a calculated or derived quantity. In this video, we are going to look at experiment 2, plotting and analyzing linear graph. At the end of the video, you should be able to develop the skill of plotting and analyzing linear graph. Or, in other words, we are going to look at how to represent the data graphically. Linear means straight, and graph means a diagram that shows relationship between two or more quantities. So, linear graph is the straight line that shows the proportional relationship between two or more quantities. In most of our experiment, we are only concerned ourselves with the linear relationship between the quantity that we are trying to investigate. A general equation of straight line or linear graph is given by the equation y equals to mx plus c. Y is the variable or the quantity that is plotted on the y-axis. X is the variable plotted on the x-axis. M is the gradient of the graph, and c is the line intercept on the y-axis, or called the y-intercept. This graph is the graph for y-intercept at 0. In the experiment, you will normally be provided with the equation that relates the quantity that you are going to investigate. For example, in the free fall experiment, the equation given to you is h equals to half times gt square. H is the release height and t is the falling time. The relationship between h and t is quadratic. We are going to transform the equation into a linear form. Y, m, x, and c. H will take the y-axis. The t square will take the x-axis. Thus, the gradient of the graph will be equals to half of g. So, to get a linear graph, you need to plot a graph of h against t square. From the equation, the value of c is 0. So, theoretically, when we plot the graph should start at the origin. But this might not always be the case due to the error in the experiment. In the projectile experiment, we are trying to investigate the relationship between the release height of the ball bearing with the range of the projectile. The equation that is given is h equals to 7 over 10 times r square over gt square. To plot a linear graph, we are going to transform the equation into a linear form. Because we are investigating the relationship between h and r, thus, h and r square will take both the y-axis and the x-axis. Rearranging the equation, we get h equals to 7 over 10 gt square times r square. H will take the y-axis, r square will take the x-axis, so the gradient of the graph is equals to 7 over 10 gt square. And the y-intercept is 0. In this experiment, we are going to plot the graph of h against r square. Moving on to the third example. This one is a little bit tricky. In the simple harmonic motion experiment, we are trying to investigate the relationship between the length of the pendulum with the period of oscillation. The equation given to us is t, the period, equals to 2 pi times square root L over G. To transform the equation into a linear form, we square both sides of the equation. We get t square equals to 4 pi square times L over G. Because we are investigating period and length, we can rearrange the equation into t square equals to 4 pi square over G times L. T square will take the y-axis, L will take the x-axis. The gradient of the graph will be equals to 4 pi square over G, and the y-intercept is 0. So, in this experiment, we are going to plot the graph of the period square against the length of the pendulum. That is the end of the introduction section to linear graph. Now we are going to discuss about the technical aspect of plotting and analyzing a linear graph. As linear graph is the graphical representation of the data, thus it is also important that you know how to properly record data in the table. For the rest of the video, we will divide the video into 4 sections. In the first section, we are going to briefly explain how to identify the number of significant figure, how to write the scientific notation, the rules for stating the significant figure at the end of addition and subtraction, and multiplication and division. After that, we will continue in the second section with table for data collection. We are going to apply the rules that we have learned in the first section when reporting the data in the table. And then we are going to look at the procedure to draw the graph, which involves the procedure to determine the axis scale, axis label, and title, plotting data point and drawing the straight line. And in the fourth section, we are going to look at how to analyze the graph. In this section, we will be looking at how to determine the gradient of the line and how to determine the experimental value from the gradient of the line. Significant figure. The first rules to identify the number of significant figure is that all non-zero digits are significant. 3761 has 4 significant figure. 3111 has 4 significant figure because all the numbers are non-zero. Second rule is that leading zeros are non-significant. For example, the number 0.002. The number has only 1 significant figure. The number 0.072 has 2 significant figure. The third rule is zeros between non-zeros digit and trailing zeros before and after decimal point is significant. The number 108004 has 6 significant figure. The zeros is sandwiched between non-zero digit, so the zero is significant. Let's say you measure the diameter of coin with a caliper 3 times. The first reading you get 0.512. Your reading has 3 significant digits. Second reading is 0.502. The reading also has 3 significant digits. Zeros between non-zeros is significant. And the third 0.500 also has 3 significant. Trailing zeros are significant. If you think about it, the zeros in the last measurement is telling you the position of your measurement. The value is measured closest to the hundredths place. That is why they are significant. Quick quiz for you. how many significant figure in the number 0.007020? The answer is 4 significant figure. The leading 0 is not significant. The zeros in between 7 and 2 is significant. The trailing zeros is also significant. So, the total number of significant figure in the number is 4. Second quiz. How many significant figure in the number 10.0? The answer is 3. The trailing zeros after the digit 1 before the decimal is significant. The trailing zeros after the decimal is also significant. Thus, we have 3 significant figure. If you think in terms of measurement, the value tells us that the measurement is made to the closest tenth. For a non-decimal number, the trailing zeros is not significant. 108000 only has 3 significant figure. The trailing zeros is not significant. But if we put a decimal point at the end of the number, for example 108000, and then we put a decimal point at the end of the 0, this tells us that the zeros is significant. The number of significant figure now changed to 6. Scientific notation is used to represent very large or very small number in the scientific form or standard index form, or for short, standard form. Also, scientific notation is very useful when we are multiplying significant number. We are going to see example of this later in the video. Okay, now let's see how you can write large number in scientific notation without changing the number of significant figure in the number. The number 12,000 has only 2 significant figure. Writing the number using scientific notation, we write them as 1.2 times 10 to the power of 4. The number still has 2 significant figure. You can just ignore the exponential power. The number 12,000 and then a decimal point has 5 significant figure. So we can write the number as 1.2000 times 10 to the power of 4. The number still have 5 significant figure. The number 0.0000214 has 3 significant figure. In standard form, we can write the number as 2.14 times 10 to the power of negative 5. We are not going to discuss each example, but I think you get the idea. In mathematical operation involving significant figure, for addition and subtraction, you are going to look for the decimal portion of the number. The result must have the least number of decimal as the number you started with. For example, let's say you have 12.01 plus 12.0344 plus 13.2 and then minus 4.505. You are going to get 41.7494. The lowest number of decimal in the terms is 1. So we have to round off the result to 1 decimal. The result of the addition and subtraction is 41.7. We are going to apply these rules when we are calculating the average value of the measurement. The average value of the measurement will have the same decimal point as the measurement. In the case of multiplication and division, you need to be concerned yourself with the least number of significant figure in the term in the calculation. Let's say you have 3.0, it has 2 significant figures, and then times with 2.03, it has 3 significant figures, you will get 6.09. The lowest number of significant figure in the terms is 2. Thus, the product of the multiplication must also has 2 significant figure. The result is round off to 6.1. Okay, another example. In this example, we are going to see how we could use scientific notation for multiplication and division. Let's say you have 23.0, it has 3 significant figures, times with 122.0, it has 4 significant figures. The result is 2806, it has 4 significant figures. The result should only have 3 significant figures, because that is the lowest number of significant figure in the terms. So, what we are going to do is we are going to write the number in scientific notation or standard form, and then we are going to round off the value to 3 significant figure. From 2806, we are going to write the value as 2.806 times 10 to the power of 3. And then we are going to round off the value to 3 significant figure. We get 2.81 times 10 to the power of 3. So the product of the multiplication between 23.0 times 122.0 is 281 times 10 to the power of 3. This is going to be your final answer. Okay, now we are on the second section of the video. I'm going to walk you through the process for reporting data and plotting and analyzing linear graph. Let's say we have done the measurement. In the experiment, we are trying to investigate the relationship between the release height and the falling time. The measurement is as shown in the table. The equation given to us is h equals to half gt square. Transforming the equation into linear form, we have h as the y-axis, the t square as the x-axis, and the gradient of the graph equals to half of g. The y-intercept is equals to 0. So, we are expecting the graph to start from the origin. Now, we are going to complete the table. Make sure you write the uncertainty for the measurement of height and time. The measurement of time is done twice, so we need to determine the average value of time. To calculate the average, we add the two readings and divide by 2. We are going to apply the addition and subtraction rules for significant figure. The number of decimal of the average reading must be equal to the number of decimal of the measurement. So the average value of time will have 3 decimal. We get the value of the average time as follow: 0.141 and then 0.2005. We round off the value to 3 decimals. We get 0.201. And then we get 0.246 followed by 0.286. And then the third one is 0.3195. It has 4 decimals. So we are going to round off the value to 3 decimals. We get 0.320. And then we get 0.348 and 0.379. We are going to apply the multiplication and division rules for the calculation of t-square. The value of the average t has 3 significant figures. Thus, the value of t square must also have 3 significant figures. We are going to round off the value of t square to 3 significant figures and write the value in standard form. If we square the average value of t, we get 0.019881 for the first reading. This is the value for the second, the third, the fourth, the fifth, the sixth, and the seventh. So, we need to round off all this value to 3 significant figures, and we are going to write them in standard form. We are going to add another column here. So, t average square. So, 0.019881, if we write in standard form and round off to 3 significant figures, we get 1.99 times 10 to the power of -2 second square. The exponential power is written at the very top column. So, you only have to write it once and it applies to all the value in the column. The second value is 4.04 times 10 to the power of -2, followed by 6.05, 8.18, 10.2, 12.1, 14.4. That is how you report your data in the table. Make sure the values are in proper decimals and significant figure. Just follow the rules that we have discussed earlier. Okay, now we are on the third section of the video. We are going to use the data to plot the graph. You have your graph paper on the left. The first step is that we have to establish the axis. You need to label the axis with the title and unit. In this example, we have the height as the y-axis, the t square as the x-axis. You are going to label the axis with title and proper unit. For height, the title is h and the unit is centimeter. For the x-axis, the title is t square or times square and the unit is second square. Do not forget to include the exponential power with the unit. It is important to note that your axis does not necessarily start from 0. You can start at any value, but make sure it has a constant interval. Okay, now on the second step. You need to choose the scale for the axis. Use a simple number for the scale. Use the number in the multiple of 1, 2, 5 or 10. You can use 0.2, 0.4, 0.6 and 0.8. They are the multiple of 2. Or you can use 10, 20, 30, 40, etc. They are multiple of 10. When choosing your scale, make sure the data point occupy at least 50% from the plotted area. For this example, we use the scale with the multiple of 10 in the y-axis and the multiple of 2 in the x-axis. Okay, now I am going to show you how to plot the data point and drawing the best fit line. The first step is you need to calculate the centroid. Go back to your table. Find the average value for x and y axis using this equation. For the x-axis, add all the value of t square and divide by the number of reading to get the average reading. Do not forget the exponential power. Your final answer must include the unit of t square, which is second square. For the y-axis, we add all the value of height and divide by the number of reading. This will give us the average height. Also, remember to include the unit for the height. This value will be your coordinate for the centroid. Coming back to the graph. The second step is to plot your data point using the cross. So this is our first data point, second, third, fourth, fifth, sixth and seventh. And then you are going to plot your centroid. To distinguish the centroid from the rest of the data point, you are going to circle the cross as shown here. So now you are going to plot your centroid on the graph. Make sure you circle the point. Now you are going to draw your best fit line. Your best fit line must be passing through the centroid and as many data points as possible. Make sure the number of data points is balanced on the above and below the line. Your best fit line does not necessarily need to pass through the origin. Next, we are going to determine the gradient of the graph. To determine the gradient of the graph, you are going to choose 2 points along the line, not on the data point, but on the line. And then you are going to draw a right angle triangle connecting the 2 points. The coordinate of the point is 1, 5 and 13, 65. And then we are going to calculate the value of the gradient. Make sure the size of the triangle is at least 50% from the size of the graph. We can calculate the gradient of the line by using the equation m equals to y2 minus y1 over x2 minus x1. Substitute the value into the equation. 65.0 minus 5.0 centimeter over 13.0 minus 1.0 times 10 to the power of negative 2 second square. Make sure to carry the unit along with the calculation. This will make sure you will get the right unit at the end of the calculation and to reduce the possibility for mistakes. The gradient is now equals to 60.0 centimeter divided by 12.0 times 10 to the power of negative 2 second square. This will give us the gradient of the graph equals to 5.00 times 10 to the power of 2 centimeter per second square. You need to convert the gradient into SI unit, into meter per second square. Thus, we left with 5 meter per second square. So, the gradient of the graph is 5.00 meter per second square. Now, we are going to use the value of the gradient to calculate the experimental value. In this case, the value of g. We have broken up the equation into linear form. The gradient of the graph is equals to half of g. Substitute the value of the gradient as 5.00 meter per second square. We get g equals to 2 times 5.00 meter per second square, which then give us the value of g equals to 10.00 meter per second square. The theoretical value of g is 9.81 meter per second square. To compare the experimental value to the theoretical value, we are going to calculate the percentage of error. The percentage of error equals to the modulus of the difference between the theoretical and the experimental value over the theoretical value times with 100%. This gives us the percentage of error of 1.94. If the percentage of error is small, means that the experiment has a high accuracy. The experimental value is close to the theoretical value. I think that is it for the video. Should you have any inquiries, please refer them to your practical lecturer. Thank you for your attention and see you in the next video.